In this video, I will show you how to work around the equation used for the exponential population growth. This equation here is used to estimate the exponential growth of population. F here stands for the future value of the population. P stands for the present value of the population. Depending on how the problem is stated, you need to adjust P to represent the earlier time. So if the problem says something like the population 10 years 10 years, so that's years, 10 years ago was 1000, today it is 1500, then you need to adjust this one, the population 10 years ago, as the value for P, the population today as the value of F. So make sure to assign the earlier value to P, the later value to F. Alright. And then E here is the Euler's constant. T is the time. If we're talking about human population, then the unit we're going to use often is going to be year. If it's like the growth of bacteria, then the most convenient unit of time, probably it's per hour. Probably it's hour, days, and then R here. This is the rate of growth. It has a unit of. It's often expressed as, for example, in terms of, like, let's say the population growth is 2%, so it's going to be expressed as 0.02. Then you need to place here. It's expressed as per time, so that means there's a unit of time in the denominator to make sure that. So again, percentage per year, and then that's going to be multiplied by t, right? So year, to make sure that the units here will cancel so that you can raise e to a value that doesn't have a unit. Just keep in mind that this one specifically has a base value of 2.718. Others, I saw some observations. I saw some other mathematical models for population growth, which uses, instead of e, uses 3 raised to rt. So it depends on the how the population growth is observed, and also the formula. If you remember the formula used for the compound interest, let's say this is per year, so raised to t. I know that there's an n here, right, for quarterly or depending on how many periods per year, but if it's going to be just per year, then the n here is removed. Actually, the equation for compound interest can also be used for expressing population growth, for estimating population growth. But for this one, let's focus on the first one that I showed you, wherein the base is the Euler's constant. Graphically, I can show you how it looks like. The x-axis here represents the time. So at the beginning, that is time 0, there is already a population present, definitely. Because whatever it is, it has to multiply, right? So we observe that it grows exponentially. Exponentially looks something like this. So let's say the population at the start is like 1000. So this is equal to 1000, and it grows exponentially. So in terms of using this equation, right, the p here is the where it intersects the y, the p. For example, if you place here, so f, p, e, the p is 1000, right? 1000. So let's say we know the r here for this particular situation. Then if you place 0 here, anything raised to 0 is 1. So this is basically just like e raised to 0, which is 1. So that means p remains, and then we get a value of 1000 here. I'm showing you this, that the p here represents where this trend line of exponential growth intersects the y-axis, sort of like this kind of analogy, but don't be confused. So this is for the straight line, equation for the straight line. B stands for the y-intercept. For this one, P here stands for where this trend line intersects the y-axis. Usually in observing the population growth, we don't know the value of R, but in order to know the value of R, we need to observe population between two different time periods. Let's say we know the population at the start, we know the population after 3 years. Let's say the population after 3 years was recorded to be somewhere like 1050. So now that we know population for two time periods and we exactly know the difference between that time period, which is 3, right? So the difference between that time period from 1000 to 1050 is 3 years, then that uh, that information allows us to compute for the R. So that's why you always encounter problems that wherein the unknown is R and then you have to apply some mathematical manipulation. And I'll tell you what it is. It's going to be logarithm, right? In order to solve for the R. So basically we have to plug in the values here, right? So 1050 is the F, P is 1000, and then E, and then R is unknown. We know the difference between time period is 3, right? So we have to clear this up by transposing. The problem here is that we have an unknown variable in the exponent, and we need to employ the rules of logarithm, wherein we're going to apply logarithm on both sides. So why do we apply logarithm? Because logarithm allows us to bring down exponent using this particular rule. For example, if you have here a power a raised to a particular number, then there's a logarithm rule that allows us to bring this down to become a coefficient and separate it here. So that allows us to bring down R if we apply logarithm both sides. There's another useful rule that we can use wherein the base here, this one I didn't place any base, so let's say base 10. For example, this one is base 10, then this one is base 10, then this is basically equal to 1. This is another logarithm rule. Basically, if the exponent is equal to the power, then this is basically equal to 1. If you're confused about this one, just remember that at some point, hopefully you did study about, I just removed the 10. Hopefully you did study about different rules of logarithm. For example, if you have a product here, then you can separate the product into the sum, into a summation. If you have a quotient here, then you can express this as the log of the numerator minus the log of the denominator. So a difference, right? So this is a rules of logarithm that we can apply to solve problems involving exponential growth, to solve problems involving unknowns in the exponent. So the best, okay, so we're going to apply logarithm both sides, but you have to keep in mind to think in advance that we want to get rid of a certain value which is e. So it is best to use logarithm base e. Because if you're going to use logarithm base e, which by the way has a special name, log base e, is also ln, natural logarithm. So if we're going to do this, first of all, we can apply this operation wherein we bring down the exponent here. So 3r log e. That's the first thing before we apply this one. So now this is equal to 1. Now we can separate this. We can solve for r by transposing 3 down here in the denominator. 1050, 1000. As I mentioned, log E is also known as ln. So depending on your calculator, you can solve for 100, 1050, 1050 divided by 1000, enter, and then you use ln. You place here ans, then enter, and then divided by 3. Or you can input this directly. So for this situation, the value of the R here is 0.01626 per year. Right, so remember this. Usually there's a follow-up problem wherein, uh, let's say 10 years from now, what is going to be the population? What's going to be the population 10 years from now? So you can still use present population of 1000. So let's see for the population 10 years from now that you know R, which is 0.01626 per year, by the way, per year, then we want to know the population 10 years from now. 10 years, we can cancel years here. This allows us to, once we know the R, this allows us to estimate the years, the population in the future. In this case, the population 10 years from now is going to be approximately 1,176, 57. There's no half population, but this is just an estimate. Now, I did mention that you may encounter exponential population growth wherein the base is not the Euler's constant. So suppose you know the future population after 5 years is 1050, same as the earlier, and then present population is 1000. You know this happened over 3 years. Let's see how we can solve for the value of R. So again, base 3, we don't know the R, we know the T. Standard procedure, we transpose. So we're left with this expression at the right side. And we want to bring down the unknown here, which is the R. So here we chose logarithm base E. For this one, we can choose logarithm base 3. Logarithm base 3. So this allows us to bring down the exponent here, bring it down as a coefficient, and then this one can be reduced to 1. So R is now equal to, and then divided by 3. So the value of R here is 0.0148 per year. If you remember the value of R using a base E, this is almost near, right? This is 0.01626. This one is 0.0148. Yeah. So probably you might deal with a situation like this wherein the base is not E. But still, I showed you this one so that you know the you will adjust the value of the logarithm, the value here, the exponent. Yeah, in logarithm, this one is called the exponent. Should I give an example for the compound interest form? Probably a quick one. So let's say same values. We don't know the R, we know it's 3. So here, we need to get rid of the 3, which we can do if we cube root both sides. If we cube root both sides, then R is already free. You can cube root this one, and then we transpose 1 to the other side, and then we're left with R. I'll just give you the value. The R here is 0.016396 per year, which is near the value we obtained using a base of E, right? So there you go. I hope this helps. As always, thank you for your support. Thank you for watching. Peace out.